Hey Chem Kids, it's Mrs. Miner, and I am going to help you learn a little bit more about Lewis structures today, and we're also going to review how to tell the difference between an ionic and a covalent bond. So, paper and pencil, you're going to notice even I have my pencil with a handy dandy eraser on it. So if you're going to do this by hand, that's how I would suggest you do it. Otherwise, you're welcome to do this on the computer using a Word document and using the draw tool on Microsoft Word. So we're going to start off with resonance structures. So resonance structures are a structure when it is possible to draw two or more valid Lewis structures for a molecule or ion. So in the last video, one of our examples was SeO2. So when we do SeO2, there's 9 pairs. So there's 8 there, and I put the last one on the middle. Now you're going to notice the selenium has 1, 2, 3 pairs of electrons and it needs 4. So I'm going to take a pair of electrons from an oxygen and move it into the middle. Now the question is, since I only need 1 pair, does it matter what side it comes from? Well, the answer before was no, not really, but the answer now is yeah, kind of. So I'm going to number my oxygen. So we have oxygen number 1 on the left and oxygen number 2 on the right. So there's 2 correct ways to draw this. One way is to draw this. Maybe I should get a pencil with better eraser, is to draw this with the double bond between the selenium and the first oxygen. The other way to draw it is with the double bond between the selenium and the second oxygen. They're actually 2 different ideas because they're 2 different oxygen atoms. So there's more than one correct way to draw this Lewis structure, okay? The more resonance structures that a molecule has, the more stable it is. In other words, the less likely it is to react with other things. So we have 1, 2 resonance structures here. Okay, well, let's do some other examples. So we're going to start off with ozone. So ozone is O3, so let's go figure out how many pairs of electrons we have to work with. So if ozone is with oxygen, oxygen is in group 16, so that gives me 6 valence electrons to work with. I'm not on the right box. Now I'm on the right box. So 6 times 3 would be 18 electrons. Divide that by 2 would give me 9 pairs. So when I draw my oxygens, okay, I'm going to call them oxygen 1, oxygen 2, and oxygen 3, just because there's so many of them to kind of help distinguish which one I'm talking about. So we're going to start by connecting everybody together. 1, 2, 3, 4, 5, 6, 7, 8. The last pair goes on top of the oxygen for 9. Now, oxygen number 1 is okay. Oxygen number 3 is okay because remember we need 4 pairs to get our 8 electrons. The oxygen in the middle has only 3, so we need to get a pair of electrons. Now, we only need 1 pair of electrons, but does it matter which oxygen we take them from? Technically, yes it does. So we're going to draw one structure where the double bond is between oxygen 1 and oxygen 2. We're going to draw it again where the double bond is between oxygen 2 and oxygen 3. Now, to show that both of these are possible structures, we're going to put a double arrow in between them, just like that, okay? And so what that double arrow means is that these 2 structures actually can exist at the same time. That's some complicated chemistry that if you decide to take HL Chem, we'll talk about in depth. But if you don't decide to take HL Chem, just be happy that you know that the arrow goes there, okay? So we're going to move down and do another example. So this one is a polyatomic ion, and you're going to notice a lot of your polyatomic ions are going to be resonance structures. So starting off with carbon. Carbon is in group 14, so that's 4 valence electrons. We did up there, we did oxygen as being 6. This time there's 3 of them, so that's 18. And then we're going to take this 2 minus ion. Remember, that means we're going to add 2 electrons to it. So that's 24 electrons. Divide that in half. will get me 12 pairs. That's all I have to work with, okay? So carbon will go in the middle because it's listed first. I'm gonna put my oxygens around there. To put my 12 pairs in, I'm gonna connect them together. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now that my outsides are okay, I'm gonna go check my inside atom. There are 3 pairs here, I need 4. So does it matter which atom I take them from? Which atom of oxygen? The left, the right, or the bottom? It does. So all 3 of them are gonna get drawn, all 3 of those options. So I have the double bond option on the left. I'm gonna put my brackets in here really quick because it is a polyatomic ion. I'm gonna draw a double-sided arrow and then go for the next option. I like to work my way around. So I could also have that double bond on the bottom. And then I'm gonna do my double arrow and draw my last option, which is to have that double bond over on the right-hand side. So now I have all of those options drawn. I'm gonna barely get it in my box there. And so there is 3 resonance structures here. So 2 resonance structures for ozone, 3 for the carbonate ion. That means the carbonate ion is more stable than the ozone molecule because it has more resonance structures. So here's one for you to try on your own. So go ahead and pause the video and see if you can get this one drawn. Did you? No, seriously, go ahead and try on your own because I make everything look easy, right? Okay, here's your answer. So for sulfur, sulfur is in group 16, it gives us 6 electrons, so is oxygen. So 6 for the sulfur, 6 for the oxygen, times 3 of them is 18, so this is 24 electrons, which will give us 12 pairs. So we're gonna put the sulfur in the middle, my 3 oxygens around it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I need one double bond here, but it doesn't matter, like does kind of matter where it comes from. So I like to start on the left and work my way to the right to make sure I get all of my structures in there. So there's my first option with a double bond on the left. Here's my second option with the double bond on the bottom. And here's my third option with the double bond on the right. Now you're gonna notice that this looks a lot like our friend carbonate. And so when we did Lewis structures the first time, I talked about, hey, you're gonna see a lot of patterns that set up. Well, this is one of them. Big difference though is carbonate gets brackets because it's a polyatomic ion. SO3 is not. Sulfur trioxide, no charge, so it does not get brackets. Okay, so those are resonance structures. The more of them you have, the more stable your molecule is. So we are going to talk about some exceptions to the octet rule. You already know one exception, and that exception is hydrogen and helium. Because they're little, they cannot hold 8 electrons. But there are some other atoms that don't follow the octet rule, and some of them will have less than 8, like hydrogen and helium, and some of them can hold more than 8, and it has to do with those pesky d orbitals that are always kind of doing some weird things for us, right? We didn't like them when we did electron configuration, and we don't like them now. So we're going to start off with ones that have less than 8 electrons. So remember, hydrogen and helium, they have less than 8 electrons because there's no p sublevel there. Boron will also hold less than 8 electrons, and the reason is because you can't make more bonds than you have electrons. It's a rule. So if we go look up boron on our periodic table, boron's in group 13, so he only has 3 valence electrons. So because we have 3 valence electrons, we're only going to make 3 bonds. Sometimes metals can form covalent bonds. It depends on the electronegativity of the non-metal. They don't require 8 electrons either. So we're going to do one example here that's BF3. So boron, we already said, is 3 valence electrons, so that's a clue that it's only going to make 3 bonds. Fluorine, come here, my friend. Fluorine is in group 17, so that's 7 valence electrons times 3, because there's 3 of them, is 21. So that's 24 electrons, which would be 12 pairs, okay? So we're going to put boron in the middle, and then I'm going to go back to my dots that I started off with when I was first teaching you Lewis structure. So see, that's 3 valence electrons for the boron. That's 3 bonds that it can form. So there's not going to be a way or a place for boron to form a double bond because it does not have a 4th electron to make that happen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Another example, we'll do MgI2. Okay. So for MgI2, magnesium, even though it's a metal, we're going to treat it like it's a covalent bond because of its electronegativity. So Mg is 2 valence electrons, so that means that magnesium will only be able to form 2 bonds. Iodine is here in group 17, so that's 7 valence electrons times 2 is 14, so I have 16 electrons, which will be 8 pairs when I'm all done. Put the magnesium in the middle. 2 dots means I can form 2 bonds. 1, 2, 3, 4, 5, 6, 7, 8. And magnesium does not have any other electrons to form more double bonds with, so we're going to be done here. And this is all that magnesium is able to do because it only brought 2 valence electrons. Now, some of them can hold more than 8 electrons, and they do that by expanding their octet. And instead of just using our s and p electrons, we're going to use the d orbitals too, because in these guys, the d orbitals are empty. So we're just going to borrow them and store some extra electrons there. And that's kind of the simple way of describing it. But some atoms can expand their octet. So if they have 5 valence electrons, so we're still having that rule, you cannot make more bonds than you have valence electrons. So if you have 2, you make 2 bonds. If you have 3 valence electrons, you make 3 bonds. If you have 5 valence electrons, you don't have to, but you can make 5 bonds. 5 bonds would be 10 electrons. If you have 6 valence electrons, you could make 6 bonds. 6 times 2 is 12. And so again, we're doing this with those weird d orbitals. Sulfur, phosphorus, and the noble gases are the most common ones that will do this. Now, you're probably like, wait a minute, noble gases, they're inert, they don't bond. We can force them to bond. It's not something we do often, but it is something that we can do. So we are going to follow the same pattern that we've been following before. So the first thing we want to do is connect. Okay? The second thing we want to do is take care of the outsides next. And then the third thing we want to do is take care of the middle atom or the central atom. So if I have pairs of electrons, the first thing they do is connect everybody together. The second thing they do is surround the outside atoms. And then the third thing that they do is go on to the middle. If the middle needs more electrons, or if there's leftover electrons, then they'll go on the middle. If the middle needs electrons, that's when we move and create double bonds. Okay, so if you can kind of keep this order, it will help a lot. So SF6, sulfur is in group 16. So that is 6 valence electrons. And then fluorine is in group 17 and gives us 7 valence electrons. So sulfur is able to make 6 bonds. Plus there's 7 for each fluorine times 6 is 42. That's 48 electrons, which comes out to be 24 pairs. Okay, because I'm dividing by 2. So I'm going to put the sulfur in the middle. So I'm going to draw 6 dots for my sulfur because it has 6 valence electrons. I'm going to squeeze my fluorines in here as best I can. And that's how many bonds I can make. So I can bond 1, 2, 3, 4, 5, 6. So I connected them together. Take care of the outsides next. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So I'm going to check all my fluorines are good. My sulfur is more than okay. He's expanded his octet. So phosphorus, PCl5. Phosphorus is in group 15, so that's 5 valence electrons. Chlorine is in group 17, and that's 7 valence electrons. So phosphorus here in the middle can make 5 bonds. Each chlorine has 7 valence electrons. 7 times 5 is 35. So we're going to have 40 electrons to work with, which comes out to be 20 pairs because nobody wants to work with 40 dots, okay? So phosphorus can make 5 bonds because it has 5 valence electrons. So 1, 2, 3, 4, 5. So the first place I put them in is to connect everybody together. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm out of pairs of electrons, so I'm going to check everybody. All of my chlorines are good. My phosphorus here in the middle is more than good. It's got more electrons than it really needs. Okay, now, what if there are extra pairs of electrons? Well, we're going to keep with our same pattern that we've been doing. Connect, outside, middle. So when we're writing these Lewis structures, there will be some pairs left over when you think you're done drawing your structure. Those extra pairs will get placed on the central atom. So let's do an example here with xenon. So xenon is one of our noble gases. So it has 8 valence electrons, and then we're doing fluorine. Fluorine has 7 valence electrons. Some of these you might even have memorized by now. So xenon has 8. 7 for each fluorine times 4 is 28. So we're going to add 8 and 28. That's 36. So that's 18 pairs of electrons. Okay? Xenon will go in the middle. And we're going to put our 4 fluorines around it. 1, 2, 3, 4 to connect them together. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So everything is full, but I have 2 more pairs. So I'm going to put them on the xenon, and I'm going to draw them like this. Put one there, and then I'm going to put one in this other corner. So they're not bonded to anything, so I'm drawing them kind of sideways so they look like they're just belonging to the xenon. And if you want yours to be on the bottom or the top and the bottom, whatever, as long as the xenon has 2 extra pairs of electrons that belong just to it. All right. So try this one. Is ICl5, so just hang tight. Oh, I will hang tight anyway. You pause the video, give this one a try, because again, everything makes sense when you watch me do it. It's when you try it that you actually start learning things. I'm waiting. Did you fast forward? Okay. So iodine is in group 17. So that's 7 valence electrons. Chlorine is also in group 17. So 1 iodine plus 5 chlorine is 6. 6 times 7 is 42 electrons. So that would be 21 pairs. I can do math. I can. So we're gonna put this iodine in the middle. It has 7 valence electrons, so it can make 7 bonds if it needs to, but there's only 5 of these chlorines here, so it's only gonna make 5 bonds. 1, 2, 3, 4, 5. So it connected them together. Take care of the outsides next. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I have one more pair, so I'm going to put it just here on this iodine. Okay, I like to call it like a little top hat because that's kind of what that looks like. All right, so that's finishing up our Lewis, taking care of our resonance, which is when you can have more than one correct answer, and we have to show them all, and our taking care of our extra pairs and our expanded octets and all of our exceptions to the octet rule. So I want to talk to you really, really quick because one of the things you're going to start seeing is your covalent and ionic smushed together, or you're going to see several of them to like in a long line of I give you names, you give me formulas, and they're all going to be mixed up. And the reason they're all going to be mixed up is we have to get used to that because when we do reactions, they're all going to be mixed up. So to tell the difference between when you're going to use the ionic rules and the covalent rules, ionics are going to have a cation and an anion. If you see a metal is a dead giveaway that you have a ionic bond. The polyatomic ions are also a dead giveaway, and so remember that's 3 or more capital letters or 3 or more symbols indicates a polyatomic ion. When you see those things, remember this lovely butterfly sheet, okay? You're gonna use the ionic bonding rules that are up at the top. If you see prefixes in the name, or you only see non-metals in there, that means we're gonna follow the covalent bonding rules. There they are. And the covalent bonding rules are where we use our prefixes. So we've got to figure out what we have in order to figure out our rules. So right here we have FeCl3. Well, Fe is a metal. So I know that I'm going to use my ionic rules. And so my ionic rules say that the metal keeps its name, the non-metal changes to IDE. So Fe is iron. I'm going to go check my periodic table and see if iron needs a charge, and it does because it doesn't have a charge written on it or at the top of its group. So I have to tell people what this charge is. So I'm going to come down here for a second. So if I have FeCl3, we started out with ions, right? The chlorine was a -1, and that 1 ended up there. And I know the chlorine was a -1 because on a different periodic table, I have all those charges written there. Apparently, I didn't grab the correct periodic table. So that means this 3 started out here as the charge. And that is going to end up as Roman numerals. So when we do reactions, if the charge of the iron changes, that's a different set of rules than if the charge of the iron stays the same. So that's why we care about the charge of the iron and not how many of those irons there are. All right, so the iron kept its name, it got its Roman numeral. I'm gonna name the chlorines, and so chlorine changes to chloride. There's no prefixes here, okay? All right, so I'm gonna figure out what it is, and then I'm gonna follow that set of rules in order to name it. So SO2, S is sulfur, and O is oxygen, and both of those are non-metals. And so if they're both non-metals, that means that I am going to use my covalent bonding rules, which is where I get to use my prefixes. So when I do this, there's 2 S's. The prefix for 2 is di, and the first one keeps its name as sulfur. Then for the second one, there's 3 of them. That prefix is tri. The second one changes its name to IDE, so that's oxide. So disulfur trioxide. All right, KNO3. See this K? K is a metal. But I also have another surprise there. See that NO3? I have a polyatomic ion too. So I'm going to start off with the K. K is potassium. Oh, sorry, that means I'm using my ionic rules. I said it in my head, but I didn't say it with my mouth. So I'm going to use my ionic bonding rules. So the first thing we're going to do is we're going to name this potassium. That's spelled wrong, you don't care. And I'm gonna check on my periodic table. Potassium is in group 1, and so it's always a +1, so I don't have to tell people what its charge is. NO3, I'm gonna go look on that polyatomic ion list. So I happen to have that right here. NO3 is nitrate. So remember, polyatomic ions are going to keep their names because we have to go find them on this list and they're kind of special, so we want to make sure that we can see them. So potassium nitrate would be my example there. So I'm going to give you these two. One of them is ionic, one of them is covalent. Again, I want you to pause the video. I want you to give this a try. See if you can figure out who's ionic and who's covalent, and then see if you can name them. Did you do it? Are you still watching? I don't know. Okay. So we're going to start here. So these parentheses are a dead giveaway. Anytime you see parentheses, that is a polyatomic ion. So these are my ionic bonding rules. In fact, both of these are polyatomic ions. NH4 is ammonium. And then my other one, SO4, is sulfate. So they're going to keep their names. So ammonium stays ammonium, and sulfate will stay sulfate. So down here, SiF4, technically Si is a metalloid, but we treat them like they are non-metals. So these are our covalent bonding rules. Or I should say metalloids bond like they're non-metals. So I'm going to name this with prefixes. I have one Si, which is silicon. I never use the prefix for one at the front, which is mono. Then I have 4, which is tetra. Fluorines changes to fluoride. So this is silicon tetrafluoride. So I hope you guys are finding this helpful. And remember, if you have questions, please email me.